Hello and welcome, class, to this Chapter 10, Part 4, our conclusion of the discussion, our introduction to enthalpy, thermodynamics, energy, all this good stuff. So in this last section, we are going to be learning Hess's law, which is a really useful way to approach calculations of reaction enthalpies. All right, so let's technically define Hess's law. I said that we've seen a little bit of it in action. This is true. So let's technically define what it is. We'll make some connections to really understand the intricacies of this. Hess's law, also known as Hess's law of constant heat of summation, means that the reaction enthalpy, our delta H reaction, is the sum of all of the enthalpies of constituent reactions. In other words, the enthalpy of our reaction is equal to the sum of its parts. Now, we've seen a little bit of this again already when we were learning how to, and we saw how to calculate enthalpy of reaction from enthalpies of formation in Part 2 of our Chapter 10 lecture. There are a couple of other ways, though, we can manipulate reactions to determine some more, let's say, technically difficult to find enthalpies of reaction. So the rest of the terms how we can use Hess's law are stated in the rules 1 through 3 below. So the principle of Hess's law is that if we add reactions together, we are going to add their enthalpies together. Point number 2 states that if we change the direction of a reaction, we're going to also change the sign of its enthalpy. And point number 3 states that if we scale the magnitude of a reaction, we are also going to scale its enthalpy. Now, this last point number 3, we've already seen also in our previous discussion when first introducing enthalpy. Specifically, we were looking at scaling reactions up or down so we could calculate magnitudes of heat, and when we scaled reactions up and down, we also scaled their enthalpies. Hess's law states that we can manipulate reactions and their corresponding enthalpies in that way for every reaction. As a reminder, a law, as opposed to a theory, is a consistent set of observations across the known universe. All right, so we're going to spend today, the better part of today, working through a couple of example problems to see steps number 1 and 2, and then also all 3 of these kind of like coming together. We're gonna learn how to manipulate what are known as constituent reactions according to Hess's law. All right, so let's find an enthalpy for this reaction. We can see that we are in this what is known as like the equation that we're interested in. There are 3 hydrogens coming together with a nitrogen to make 2 ammonias. We do not know what the enthalpy of this reaction is. However, we are given 2 constituent reactions. And again, this language of constituent reaction implies that these are 2 like lesser reactions, and we can in some way add these 2 things together to get the reaction that we're curious about. So let's see how we can do this. In this first problem, right, in trying to find the enthalpy of our overall reaction, we're just going to see Hess's law, the first step of Hess's law, in action. So step number 1 states that if we add reactions, we add the enthalpies. So let's add these 2 reactions together and see what happens, right? We're just seeing what happens here. Well, when we add 2 reactions together, what we do is add all of the reactants up and add all of the products up. We're then going to like combine some species together that can be combined. We can cancel some things out, but let's just start at step number 1, right? We're gonna add things together. Well, if we add all of the reactants up of these 2 constituent reactions that are given to us, we can see that there are 2 hydrogens in gaseous form, a single nitrogen in gaseous form, another hydrogen in gaseous form, and dinitrogen tetrahydride, N2H4, also in gaseous form. all of these reactants come together to form N2H4 as a product, as well as 2 ammonias. All right, so we can see that N2H4 is both a reactant in the second reaction and a product in the first reaction. When we add the 2 constituent reactions together, what it appears is happening is that one of our reactants is just hanging around and is not turning into anything else. It's not actually involved in the chemical reaction, or so it would appear. What this means is that we can cancel out the N2H4. If it's present on the left and on the right, we can cancel it out in much the same way that we canceled spectator ions from total ionic equations to get a net ionic equation. There's something else we can combine together. We have 2 hydrogens and a single hydrogen, both kind of separated, but nonetheless present on the reactant side. So we're gonna merge those together, right? 2 plus 1 is equal to 3. So we have 3 hydrogens in gaseous form, N2 as a gas, and this is transforming into 2NH3 gas. Well, this reaction that we got from adding up the 2 constituent reactions looks the exact same as the reaction that we're trying to find some pieces of information about. So it would appear as though these 2 constituent reactions we can almost think of as like step 1, step 2, right? If you want to get the overall chemical reaction here, first we're gonna have to take 2 hydrogens and a nitrogen to make this kind of like intermediate product. We're gonna add another part hydrogen to it, and voila, we have NH3. Specifically, we have 2 of the NH3s. Well, if these 2 reactions, when added together, give us the overall reaction that we're curious about, what this means is that if we add up their enthalpies, this is going to give us the measurement for what the overall enthalpy should look like. One way that we can think about this is in the same way that we saw like the energy diagrams for exothermic and endothermic reactions before. If we have energy on the y-axis and time on the x-axis, we can think of our reaction or reactants as starting in a certain place, and over the course of our first constituent reaction, there is an endothermic reaction that gives us a certain amount of products. Energy level is going to be higher than that of the first set of reactants. Right, here's our 2 H2s and our N2 coming together. This gives us our N2H4. Well, according to our second reaction, if we combine this N2H4 with another H2, we're going to get a second reaction, and this second reaction is going to be exothermic. So we're going to draw this reaction as exothermic, where here the reactants are higher in energy than the new products all the way down here. And our 2 products are going to be our 2 NH3s. 2NH3. So what we're ultimately looking for is what's the energy difference between our reactants and our products. We can forget about all of the in-between steps. We're just looking for the net difference here. And the net difference is going to be equal to the sum of these 2 enthalpies corresponding to step 1 and step 2 in this chemical reaction. All right, so if we add 95.4 to negative 187.6, our total calculated enthalpy is negative 92.2 kilojoules per mole. But this is not the only rule in Hess's law, right? This is only the first. If we add reactions, we add enthalpies. This is the most straightforward approach, because no matter how many constituent reactions go into the overall reaction that we're curious about, the last step is always going to have to be to add the reactions up and add the enthalpies up. Things can get to be a little bit more complicated, though, when we have to get a little creative, when we have to employ the other 2 rules in Hess's law. All right, so let's look at another problem. We're still ultimately looking for the same thing. We're given an overall reaction, and we're asked to find its enthalpy. There are 2 constituent reactions below. So we can try and take the same approach as what we did last time, But we would run into a little bit of a snag. You see, in the first reaction, we have sulfur coming together with oxygen, and in the second reaction, there's an SO3 here. Specifically, there are two SO3s. The products that are given by the constituent reactions are SO2, another two SO2s, and an oxygen. Well, when we look at the overall reaction that we're trying to figure something out about, it appears as though the SO3s are on the product side, and there are no SO2s anywhere. So what this tells us is that we're going to have to manipulate these constituent reactions before we can add them together and get anything meaningful. So how we can more, let's say, consistently or like systematically approach Hess's law to solve these types of problems is by first picking out in the constituent reactions where the reactants and the products are in the overall reaction that we're curious about. All right, so I'm going to clean this up a little bit. The sulfur, we can see in the overall reaction that we're trying to learn or predict something about is on the reactant side. So what we're going to do is kind of circle or box where all of the sulfurs are in the constituent reactions down below. We can see that there is a sulfur, also in gaseous form. Phases matter here. This sulfur in gaseous form is present on the reactant side. However, there are two of them in the overall reaction, and there's only one of them in the constituent reaction. Well, this is a huge red flag. This means that in the constituent reaction, we only have half as much sulfur as what there needs to be. And when I say needs to be, I mean, this is the goal, right? Again, we're trying to figure out something about this unknown equation. We're trying to figure out what its enthalpy is. If we want to determine this equation's unknown enthalpy, we need to make sure that all of the reactants and products are not only present, but present in the correct amount. Otherwise, these reaction enthalpies here will not be giving us anything super meaningful. So in order to make sure that the constituent reactions contain the proper amount of sulfur, we're going to scale this reaction up by a factor of 2. Just to go backwards, here, if we scale the magnitude of a reaction, again, this is bullet point 3, we're going to also scale its enthalpy by the same factor. Now, we've seen this before. Again, when we were trying to figure out enthalpies of formation, we were calculating an enthalpy of reaction. We had to scale in that case, we were scaling everything down by a factor of 2. Here, we're doing the opposite. We're scaling up by a factor of 2. So the sulfur, we're going to have 2 of them. Our oxygen, we're going to have 2 of them. In this SO2, we're going to have 2 of them. And since we scaled the constituent reaction up, we're also going to have to scale the enthalpy up by a factor of 2. If we scale the enthalpy up by a factor of 2, this means that our new reaction, that's twice the size, is also going to have twice the enthalpy, equal to 594 kilojoules per mole. All right, that's well and good. We have 2 sulfurs now. Let's turn our attention to the next reactant in the overall reaction. I'm going to change color quick. Want to make sure that my color coding is going to be useful here. It seems as though in the overall reaction we have 3 oxygens. So let's circle where all of the oxygens are in the constituent reactions down below. Well, we have 2 of them here. That could be a little bit of a problem because, again, we want the coefficients to match, but we already know that we can't change anything about this first reaction because these 2s in front of the sulfurs need to match. So hopefully there's an oxygen somewhere else. Kind of looking around. Aha, here we go. 2 plus 1 is 3. But there's an issue here. In the first reaction, the oxygen is on the reactant side. In the second reaction, it's on the product side. We know that we want the oxygen to be on the left hand or the reactant side in these 2 constituent reactions in order to get some information about the overall reaction. So what we're going to do is flip the script. We're going to reverse the direction of the second constituent reaction to make sure that all of the oxygens we need are on the left-hand side. So our 2 SO2s in gaseous form and our single oxygen are going to be on the left. These are going to transform into 2 sulfur trioxides, which will be in gaseous state on the right. So this we don't care about anymore. The blue reaction down below is written in the proper form. Since we reversed the reaction, we must also reverse the sign of the enthalpy. So what used to be a positive 198 kilojoules per mole is now going to be a negative 198 kilojoules per mole. This gives us 3 oxygens on the left-hand side of the reaction if we were to add up constituent steps 1 and 2, which aligns with the overall reaction that we're curious about. All right, and last but not least, I'm gonna change to, where is it? There, green. Bright lime green. Sulfur trioxide should be our product, which means all of the sulfur trioxides in the constituent reactions should be on the right-hand side, or add, cancel appropriately. In the first constituent reaction, there is no sulfur trioxide. In the second constituent reaction, it appears as though flipping the reaction, as we already have, also presented the product on the product side of the constituent reaction. So we were kind of working ahead a little bit, but it was exactly what we needed to do. So there's no other manipulation we need to do to get our SO3 on the product side. It's already there now. All right, so the individual manipulations of the constituent reactions is complete. The last thing that we should have to do is add up these reactions, and everything that we want to cancel should cancel. Everything we want to be present should be present in the proper magnitude. So if we add, before doing that, I'm gonna change color because this lime green is vicious on the eyes. Let's add the 2 constituent reactions together. So first we have 2 sulfurs in gaseous state. Next, we have 2 oxygens in gaseous state. Then, again, we're down here, we have 2 SO2s in gaseous state, which is not present in the overall reaction, but have no fear. For as we start writing out the products of this reaction, we can see the first constituent reaction gives us 2 SO2s in gaseous form. The other product in the second reaction is 2 SO3s in gaseous form. Just like the previous example, we are going to cancel out species that are present on both the left and the right-hand side. So both of these SO2s are going to disappear. If it's present on the left and the right, what this symbolically means is that it is not technically involved in the overall chemical reaction, so we can get rid of it. It may actually physically be involved in the chemical reaction, but for the sake of energy, it's not here, it doesn't matter. Just like net ions just like spectator ions in the net ionic equation. Again, I'm gonna use that as the parallel. We can see that there are 2 different sets of oxygens here on the left, so I'm just gonna change this coefficient to 3. Since 2 plus 1 is 3, I'm gonna merge them together. And now we can see that the overall reaction with 2 sulfurs and 3 oxygens on the left, 2 SO3s on the right, matches that of the overall reaction we're curious about. So the last step that we need to do is to add the 2 constituent enthalpies up, and this will give us the overall reaction enthalpy for the hypothetical reaction in question. So if we take negative, I just realized there's a negative sign here, negative 594, and subtract out 198, this gives us a total enthalpy of negative 792 kilojoules per mole. If you caught that before I did, like, kudos to you. There should be a negative sign over here. I'm so sorry if there was lingering confusion. I caught it in the end. Both of our enthalpies are negative. The first because it's just naturally exothermic. The second because we reversed the constituent reaction. And that is the gist of Hess's law. If we have any number of constituent reactions, whether it be 2 steps, like in these couple of examples, or more, the best way to approach the problem is to make sure that the reactants are where they need to be, the products are where they need to be in the constituent steps down below. Make sure that you rearrange any remaining equations such that species you don't want get canceled out. And then when you're all done, you can add everything together, and this gives you an overall calculation for what this hypothetical enthalpy is for the hypothetical equation. Let's talk about lattice energy. So lattice energy is the amount of energy represented by variable U required, technically speaking, to convert 1 mole of ionic solid into constituent ions in the gas phase. Ooh, that's a bad underline. There we go. All right, so why 1 mole of an ionic solid? Why are we converting it into ions in the gas phase? Well, what this difference represents is the total amount of energy contained within an ionic crystal. The energy contained between a sodium plus and a chloride minus is the bonding energy. It's the amount of energy holding these ions together. So what better way to find the total amount of energy between them than by observing the difference in energy between a sodium chloride crystal and that of the sodium chloride totally broken apart. Right, the difference between these two energetic states is equal to the chemical bond between them. Now, finding lattice energy, as is described in many textbooks, is pretty complicated. For instance, in this diagram here, what is being demonstrated is a roundabout way to find what U is equal to. Again, lattice energy. The reason why is, the reason why we have this roundabout way of finding lattice energy is taking an ionic crystal and not only vaporizing, but ionizing it can take a lot of energy. It can take expensive materials and instruments in order to really be able to finesse and tell how much energy exactly went into it. So instead of taking the direct approach, we take this roundabout approach. Taking this roundabout approach may appear in this diagram to be complicated, but physically it's actually easier. So I'm gonna clear the slide a little bit just so I can draw more on the diagram and the arrows won't be in the way. Shift E. So what we're gonna start with is the description of this energy gap here. We're just gonna describe each of these energy gaps in turn. The first energy gap is what we know as the enthalpy of formation of sodium chloride. And we've defined the enthalpy of formation already. We take the two, or all of the reactants in their pure elemental form. So sodium solid is the pure elemental form of sodium. We're gonna add this to 1/2 chlorine gas, which looks a little strange, but again, we want to make sure that the product, which is sodium chloride, has a coefficient of 1 out in front. We've talked about this in chapter 10, part 2. The energy difference between the natural state and the lower energy state of sodium chloride gives us the enthalpy that is required to form, hence enthalpy of formation of sodium chloride, which we can see specifically here. Well, if instead of starting with sodium chloride, we start with these elements in their natural form as well, would this not seem like the first step in trying to chemically ionize these species? Right, if we want to take sodium chloride and break it down, wouldn't the first step just be taking the natural reaction and doing it in reverse? Physically in the lab, that's actually pretty complicated, but on paper, it's super easy, right? If we reverse a reaction, we reverse the enthalpy. Easy peasy. And from here, we're just going to alternate between ionizing and vaporizing. So the next energy gap we can see here, the only difference between the reaction that's down below and the one up above is that we've taken sodium in its solid form and we have vaporized it. This we know as an enthalpy of vaporization. You don't have to worry too much about all of these subscripts that are here. I just am using these subscripts to point out the different forms of chemical reaction that we are undergoing. So we can see that we added a certain amount of energy per every mole of sodium that we have vaporized. And the next step upwards is to take our Cl2 and actually cut it in half, right? We only want 1 chloride ion. And so to do this, we are going to break the bond between our 2 chlorines presented here. So the chlorines that are bonded together are going to contain a certain amount of energy or enthalpy that we are going to have to break. And this enthalpy is known as the binding or bonding energy. So we're going to cleave these chlorines in half. So we've taken the sodium from solid form and turned it into a gas. The chlorine, which already existed as a gas, we just cut it in half. Now we have gaseous sodium and gaseous chlorine. The next step is that we're going to have to take an electron away from our sodium. We're going to have to ionize it. That is the next step in energy as we move our way upwards, the enthalpy of ionization energy, or IE. Remember back from first semester, I think it was chapter 4, we first defined what ionization is. Technically, ionization is a species losing an electron to become a cation. So the ionization energy that is presented here is specifically for sodium losing its electron. And this last step we can see here is actually exothermic. We are lowering the energy of the overall state of things. We're lowering the energy of our chemical species by taking the electron and giving it to chlorine. Now, the reason why this is an endothermic process in this case is that the chlorine really wants that electron, and in fact, to form bonds, we must lower ourselves in energy. The same thing tends to happen with electron affinities. This enthalpy corresponds to that of an electron affinity. The chlorine is gaining an electron and lowering in energy. So instead of taking our sodium chloride, heating it up and shooting it with a bunch of electrons to ionize them, we instead looked at the reverse of our enthalpy of formation equation and then took this roundabout approach, subliming our sodium, breaking apart our chlorine, ionizing the sodium, ionizing the chloride. All of these energetic pieces along the way we can use to figure out or calculate what the lattice energy of sodium chloride is. Because the energetic levels are presented here, we can pretty easily visually see what we need to add and subtract. We need to add together all of these enthalpies to give us this net height, and then we're going to subtract out the enthalpy for our electron affinity. So we're going to take a positive 411 kilojoules per mole, positive because we reversed the direction. If you remember, we're going upwards now, upwards instead of downwards, so this should be a positive value. We're going to add 107, we're going to add 121, we're going to add 502, and then we're going to subtract the difference of our enthalpy of electron affinity. This will give us the question mark value here, this U, this lattice energy. And in crunching these numbers, what we would find is that the lattice energy for sodium chloride is 786 kilojoules per mole, according to the values presented in this diagram. Now this way, this diagrammed approach, is the way that the textbook instructs on how to solve for lattice energy. The textbook says that we always need to add together our enthalpies of formation, vaporization, binding energy, ionization energy, subtract out the electron affinity, and there you go. But let's turn away from our ionic complexes and turn to their covalent brethren. Since covalent compounds / molecular compounds are not held together by infinite crystal lattices, we're going to have to take a little bit of a different approach to figure out what the bonding strength is inside of a covalent compound. This we call bond enthalpy. It is the strength or energy contained within one covalent bond. Bond strength is also synonymous with bond enthalpy in this case, so we're looking at the energy needed to break 1 mole of a particular covalent bond type inside of a molecule. The enthalpy of a reaction can be found by using these theoretical bond strengths. So this is our last equation to learn in the chapter. We've learned so many already, but here is a new way to find the enthalpy of reaction. If we know the theoretical amount of energy of the bonds contained within the reactants, we can assume that all of these bonds are going to be broken, we're putting this energy in to break bonds. Hence the positive enthalpy here, since there is a kind of an implicit positive sign. We're also going to then subtract out the energy of the bonds forming on the product side. The energy of the bonds forming is energy released. Right, a way to think of this is as a molecule is coming together, as bonds are forming, the molecule's relaxing, right? Bonds want to be made. Atoms want to be stabilized by covalent bonds. And so we can kind of get this mental image of like an atom like relaxing back in a hammock, just letting itself chill for a little bit as it's now being stabilized by a covalent bond. As energy is being released while bonds form, this is going to correspond to an exothermic process and a negative enthalpy. Hence why there is a negative sign here. So the energy released that's getting plugged into this equation is, the magnitude of the energy of the bonds being formed are always recorded as positive values, because this negative sign here is going to take the energy being released kind of perspective out of critical thought. So the equation is set up that in such a way that you don't need to manipulate the magnitudes of the bond enthalpies. We just plug them into this equation. The equation takes care of the sign. So let's wrap up today's lecture with one more calculation, one more problem. We're going to find the enthalpy of reaction for the following reaction using average bond energies or average bond enthalpies. Now, I don't have a table of the bonding enthalpies presented here. I'm going to give them as we go. But what's really important here is that we are not only paying attention to what molecules are present, but what bonds are present. We need to know how these atoms are connected. So we're going to have to dust off our Lewis structure drawing skills in order to piece together what bonds are present where. So N2, I'd advise you at this point, kind of take a break, draw the Lewis structures for yourself, make sure that your skills are sharp. I am just going to, keep charging ahead. So if you'd like to get some practice, please pause the video. I'm just going to keep moving forward. N2 has a triple bond between the two nitrogens, two lone pairs on either side. Each of these H2s is held together by one single bond between the hydrogens. Do this like that. And our ammonias each contain a nitrogen bonded to each of these hydrogens with a lone pair on the nitrogen, and of course we have two of them. So notice that I'm not just drawing one of the molecules, I'm drawing all of the molecules according to our stoichiometric coefficients. This matters. The reason why this matters is because, again, we are not looking at the enthalpies of a molecule, but the enthalpies of the bonds within the molecule. So according to theoretical research, the average energy between a nitrogen-nitrogen triple bond, or I should say within a nitrogen-nitrogen triple bond, is 941 kilojoules per mole. And the theoretical energy within a hydrogen-hydrogen triple bond is 436 kilojoules per mole. And last but not least, the energy inside one of these nitrogen to hydrogen single bonds is 388 kilojoules per mole. So again, notice these enthalpies do not pertain necessarily to the whole molecule, but rather the bond. So when we use our previous equation to find the reaction enthalpy, we're going to have to add together the sum of all of the energies from the reactant side, all of the energies of the bonds being broken, and then we're going to subtract out all of the enthalpies of the bonds being formed. All right, so we're going to break one nitrogen-nitrogen triple bond, which gives us 941 kilojoules per mole, presented here. we're going to add to that 3 times 436. The reason why we're multiplying this by 3 is because we have 1, 2, 3 hydrogen-hydrogen triple bonds present on the reactant side of this equation. There are 3 sets of hydrogen-to-hydrogen single bonds being broken. So we're going to have to put in this much energy 3 times. All right, I'm going to continue the equation down here. I'm going to circumvent these hydrogens that I have drawn. So I'm going to now subtract out the magnitude of the energy that is being released, the amount of energy coming together from bonds being formed. Well, we can see on the product side, we are forming 1, 2, 3, 4, 5, 6 different nitrogen to hydrogen single bonds, which means we're going to subtract out 6 times 388 kilojoules per mole. All right, big equal sign, so I can draw the final answer over here, kind of in this empty space. The predicted enthalpy of reaction by observing the bond enthalpies for this reaction is negative 79.0 kilojoules per mole. And so here's how we can use the equation that we just saw on the previous page. Again, notice that I did not manipulate the signs explicitly on any of these bond enthalpy values because the equation takes care of that for me. So long as you're plugging in the values for bonds breaking on the left-hand side, because this is an amount of energy we need to put in, versus bonds forming at the end, the negative sign that is kind of, well, explicitly in the equation will take care of the sign of the energy needing to be released. Okay, that's cool. So we have now a bond enthalpy of negative 79 kilojoules per mole. Something else I want to touch on before we call it a day is the fact that bond enthalpies tend to be found by theoretical / computational means. That's not to say that, some bond enthalpies aren't found experimentally, but there tends to be some theoretical or computational approach to finding bond enthalpies nowadays. The reason why I want to bring this up is we've actually found the enthalpy of reaction for this very same reaction a different way earlier in this lecture. Right, our very first example of Hess's law, which now the slide looks like a mess, we found the enthalpy of reaction for the exact same reaction using constituent reactions instead of bonding enthalpies. And we found a similar enthalpy, but it's not the exact same. So here, by observing other experimental observations, by adding together these constituent reactions, we have an enthalpy that looks different. It's negative 92.2 kilojoules per mole, as opposed to the one we just found with bond enthalpies, which is negative 79. Now, in the grand scheme of things, that's not a huge magnitude of difference, but I want to acknowledge where the difference comes from. The enthalpies here that we found from Hess's law were experimentally gathered. So there is a little bit of a chance for experimental error. There's a little bit of a chance for human error, for instrumental error. So there are some sources of error in the implicitly whenever experimentally found values are found. However, that's not to say that the bonding enthalpy approach is totally innocent either. Theoretical / computational approaches always take averages. We're always looking at statistical averages and approximations. So the negative 79.0 kilojoules per mole isn't 100% accurate either. In fact, the real bonding enthalpy of reaction is probably somewhere in between these two values, within standard means or standard deviation. So I want to point this out. If you are working, through a homework problem, you look up a bonding enthalpy or a constituent reaction or something online, and if you're not finding super consistent or 100% consistent results, this is probably why. There's going to be some type of averaging or approximation involved, whether it comes from experimental error or if it comes from computational averaging. Not every reaction enthalpy is going to be the exact same. And so we have to use a little bit of critical thinking. How close are the values? Does it make sense? Am I in the right ballpark? This is going to be something that we grow to be increasingly comfortable with during this semester, is being able to critically evaluate our work and to be able to say, yes, this is correct because I'm in the right ballpark, or no, I am not in the correct ballpark. I'm gonna have to go back and make sure that I didn't add a minus sign or drop a minus sign, especially because signs are so important here, and it's very easy to accidentally drop a minus sign or forget a coefficient of 2 or 1/2, whatever it may be. And with that, we are finished with chapter 10. So here we have some suggested example problems. Again, I don't collect these, so feel free to work on these at your own pace if you would like to. We have some Hess's law problems, so getting comfortable with those rules 1, 2, and 3 and how we can manipulate enthalpies. We have some bonding enthalpy problems, so these pertain to the covalent compounds, looking at bonds breaking and bonds forming. Last but not least, we have lattice energy, which you can use either the diagram or the Hess's law approach, whichever you are more comfortable with. All right, if you have any questions and you're in my class, do not hesitate to shoot me an email, come to office hours, whatever it is you need for clarification. If you are not in my class, please feel free to drop a comment down below. If you have any homework, do your homework, and until next time, class is dismissed.